Yeah, thank you, Johannes. Thank you for the invitation. Well, first of all, I wanted to say that it's actually very nice to lecture after Bernd. I found it actually interesting. Is an interesting thing to notice. I mean, I'm a physicist, of course, and he's a mathematician. And of course, he started saying this lecture today was the most difficult of all the lectures he's going to give. For me, it's probably the only one that I will understand, I fear. Let's see what happens tomorrow. Because, of course, I mean, we think about the same things in very different ways, right? And of course, we are used to this kind of language. So my hope is that my lecture will be easy enough. I mean, I think I actually have to apologize to, I see some people there that, I don't know, you will be bored. Sorry about that. But I will try also, one of the goals of this lecture is maybe to share with you the type of language that we use when we talk about Feynman integrals. You will see that physicists, with respect to mathematicians, as you probably already know, we have a different approach, which is typically we go from special examples and then we generalize without really proving so that things really work. I mean, we convince ourselves that it works in a special example and then we assume it always works, right? This is what we do. So you will have to put up with that, right? But hopefully most of the things that I will talk about are relatively reasonable. The one thing that will be a little bit strange, maybe if you have never seen it before, is that I will talk about Feynman integrals in d dimensions, the same d dimensions that Bernd talked about in defining his kinematics. But these d dimensions for me will be a complex variable. Okay, so we're actually going to think about continuing in d dimensions these integrals because otherwise they are not convergent in 4 dimensions, or in general in even numbers of dimensions they might not be convergent. And there is a procedure that is called dimension regularization to do this. I don't have time to prove this and how it works exactly, but I think once we go through the lectures, in particular tomorrow, maybe you will see that this is actually much simpler than it looks from the formulas that I will write today, because today I will write some formulas where maybe you say, okay, this D, what does it mean and how can I make sense of that? This will become a little bit more clear, I think, tomorrow. Okay, so a bit of introduction. I'll try maybe, I don't know if I should use also this board, but I can maybe try to write here. Yeah? Well, let me try to start here and then let's see. There are a lot of blackboards. This is like more central. So why are we interested in Feynman integrals? So Feynman integrals are integrals that appear in many different types of calculations that we do in physics. Typically, I mean, they appear in quantum field theory, so a theory that is based on quantum mechanics and relativity, when we compute scattering amplitude. These are really probabilities, is a way to compute the probability that a scattering process happens. So typically we draw them in very schematic ways like this. We have some particles that come in, something happens, some particles that go out, and we want to compute the probability that the scattering happens. So we will have some kind of funny drawings like these ones, where the type of particles that we draw depend on the identity of the particles. If it's a scalar particle, if it's an electron, so it's a spin 1/2, if it's a photon, so it's a spin 1, and so on. So this is the classical place where we find Feynman integrals. But they also don't just appear here, okay? Feynman integrals, for example, they appear also very naturally when we study so-called effective field theories, where we actually compute things off shell. So in this particular case, these quantities are on shell, which is the proper place where the variables that Bernd was introducing make sense, because we have this momenta that respects some particular constraints. For example, pi, the momenta squared of these particles, they are equal to 0, right? In the case of Bernd, but they could also be equal to their mass. This is when something is on shell. But also the very same things appear also in quantum field theory when we compute off-shell things, so green functions in general, in jargon, in a sense. And effective field theories are an example of that. We definitely use Feynman integrals, and we have to do this kind of calculations in order to match theories at different energy scales. Also, they appear very strangely in classical physics, in some sense. Classical in a sense of non-quantum. When we compute gravitational waves corrections, gravitational waves production and scattering, this was a very interesting development that people realized that one can do some classical calculations in GR, so in gravity, which is completely classical, but it actually turns out that these calculations are simpler if you do them in a setup that is simpler to quantum field theory and produces some sort of Feynman integrals, and then you take kind of the classical limit of this. And also, I mean, Feynman integrals or Feynman integrals-like objects, they also appear really when we compute so-called physical cross-sections, which correspond practically to the square of the scattering amplitudes. They really give us the final physical probability of the scattering process to happen. So they appear in many different places, okay? And somehow the interesting thing is that these Feynman integrals, so they are so important, they are so central, and in all these different, even if they look a little bit different, depending on where they come from, many of the mathematics that is behind them is actually similar, and is also one of the reasons why there has been so much crosstalk in the last, I would say, 20, 30 years, but it's becoming more and more with mathematicians to try to understand. Well, we physicists are trying to understand what can we say about these integrals that maybe mathematicians already know. And of course, that's where things become interesting, because just understanding the language, right, between us is difficult. But we are discovering a lot of interesting stuff connected to these integrals. In particular, we will see a connection somehow of these integrals to geometry. Hopefully, I will manage to get there towards the end of these lectures, which is a little bit different than the geometry that Bernd talks about, because he's talking about constructing, if you want, the integrand, which is the object that we integrate, while I'm interested about what happens after I do the integral, okay? But of course, the two things must be connected somehow, and this is one of the most interesting parts to try to understand. So from a point of view of physics, okay, maybe let me try to push this up. When we compute an integral or an amplitude, okay, we typically draw something like this. You will see in a second a little bit better some other examples of this. This is what we call, for example, a box integral. This corresponds to something where, for example, we are imagining two particles going in, for example, and two particles going out. I can put some arrows so that this becomes a little bit more clear. And you see that I have some momenta of the particles. So there is, of course, in physics, we always have momentum conservation. So P1 plus P2 has to be equal to P3 plus P4. This is momentum conservation. And one of the important things is that, of course, whenever a particle comes in what we call a vertex here in one of these graphs, then it splits, you see, in two other particles, and momentum has to be conserved at all these splittings, because these are really physical processes. We think about these things as really physical processes. There is a particle that comes in and splits somehow into two particles, or it could be maybe it interacts with a particle that goes in this direction, and so on. And we can keep on imposing momentum conservation at all these vertices. So we have a momentum that goes in, that starts going around here, and then it becomes k plus p1, for example, and then here becomes k plus p1 plus p2, and then here it becomes k plus p1 plus p2 minus p3, and then it becomes k again, right, through momentum conservation using this relation. But you see that I cannot completely fix one of the momenta by momentum conservation. So whenever I draw a diagram like this where there is a closed loop, this is what we call a loop diagram, then there is a momentum k, which is free, right? And this momentum is the momentum that we have to integrate. Typically, in 4 dimensions, we try to integrate over this momentum. This is what Feynman rules tell us. I cannot really prove this for you, but just to say where these integrals come from. And the problem is that when we try to do this integral over this momentum, typically the integral diverges. And so we are going to actually generalize this, and I'm going to write things like this, where I mean that I'm doing the integration in d dimensions. For now, this for us is just going to be a symbol, okay? Because this d, as I said, can really be thought about as a complex number, okay, in principle. We will see when we do parametric representation of Feynman integrals what this really means. There it becomes really clear in which sense d can be thought about as a complex number. For now, it's just a symbol, and you can think about this as an operation. If you want a functional that acts on a function and gives you another function in some sense. Okay, so this is just to give you a little bit of notation of how we are going to draw about, how we're going to talk about these Feynman integrals, okay? And somehow one important thing is that when you try to do a calculation of this type, and this is where we are going to get, hopefully, towards the end of these lectures, you typically find general structure. So let's call this I. This is an integral, right? We compute it, and then we're going to find something that looks like this, typically. We're going to find the sum, I don't know how many, over some objects, which I'm going to call R, and they are kind of, let's say, rational functions. They might also be algebraic or actually even more complicated, but for now, let's think about rational functions. And then some FIs, which are instead transcendental functions, okay? So this is the first picture that I would like you to have when you think about the Feynman integral. When you do the calculation, you will get something like this. These are typically rational. It could be more general, okay? But for now, let's think about this case. And these ones are instead transcendental. What I mean with that, well, there could be really, I don't know, 1 over x, something like that in a variable x, and here there could be a log of x, log of 1 plus x, or something like that. And somehow this picture, this object with this separation, which seems pretty obvious, right? From a mathematical point of view, it's pretty obvious. I mean, I do a calculation, I do an integral, I'm going to get rational functions and transcendental functions. There is nothing particularly profound in this. What is actually profound for us, for physicists, is that rational functions and transcendental functions have, from the physics point of view, a very direct physical interpretation. In particular, what we know from physics, what physics tells us, is that the scattering amplitudes, and therefore I would say also integrals, Feynman integrals in general, with some caveats and some one has to pay a little bit of attention, can always have poles and branch cuts in the variables they depend on. What are these variables? Well, these variables are what Bernd called the Mandelstam invariants. And the masses. Right, so remember, you have an amplitude, you have a scattering process, you have some momenta that scatter and produce something else in the final state. So you can produce all these Mandelstam invariants, which is what typically are called SIJs, so something like Pi plus Pj squared, which in a special case where the momenta are massless, so if massless, would be equal to 2 pi dot pj, but in general there is also another piece, right, if the momenta are not massless. And then of course they could be masses, because these particles here that run around here, they could have their own mass, and so there will be a dependence also on the mass of those particles. Now in this set of variables that the amplitude depends on, so let's call it, maybe I called it I, my integral, so it will be a function of all these SIJs and possibly of the masses squared. This function will have poles and branch cuts, right? And these poles and branch cuts in these variables, they're actually fixed, they are not random, okay? So it turns out that physics tells us that poles correspond to single particles going on shell. I'm going to make an example now, so this becomes a little bit more clear, possibly. And branch cuts correspond to multiple particles going on shell. What do I mean with this? I'm using this language, which maybe for mathematicians is a bit strange on purpose, because I want to actually get you used to that, because I'm going to use these words, okay? So imagine what is the simplest Feynman graph that I can imagine of drawing with an integral, for example. I could have something like this, right? This is an example in a specific theory where I have like two particles that go in and then two particles go out, right? And then you see that now this looks a little bit different than the one that I have here, because I have different possibilities. So you see these particles have momenta P1 and P2 that come in, right? Let me draw it. Yeah, of course. Yeah, exactly. I'm going to get there. That's why I want to explain exactly what I mean with that. So what does it mean with branch cut? So let's look at this example. That's why I wanted to do the example, so that this hopefully becomes clear. So imagine that you have a situation like this, okay? What Feynman rules tells us for something like this is that whenever there is a line, like this one, this line corresponds to the propagator of this particle, which is just a rational function. So if this momentum is P1 plus P2, which I'm going to call S12, the square, this is just going to be 1 over S12 minus possibly its mass, if this particle has a mass. Okay, this comes from Feynman rules. So you see that now this, in this diagram, okay, I cannot really prove the Feynman rules from you, but you have to believe that. That's how you build these diagrams. You see that whenever there is a single particle here, that what does it mean can go on shell? It means that the energy of these two particles is equal to its mass. So I can actually produce it in physical sense. I have exactly the right energy to produce this particle. Then in this object here, I can produce a pole, right? A singularity. This is what I mean really with a pole. What do I mean instead with a branch cut? Yeah? So the one before, so on shell can be anything, right? It just means that the external particles are on their mass shell, right? So if they, in the case that Bernd was discussing, he had only massless particles, so it would mean that all the PIs are equal to 0. But in general, it would mean that the external PIs are equal to their mass. Right? You could have, for example, an electron as a mass that is different from 0. So when it's on shell, it means that I'm really scattering with an electron that comes in here, and this particle, so this pi squared, is equal to the mass of the electron. In general, I don't have to do this because these are analytic functions, so I can consider them for a general value of the pi, which is not on its mass shell. This is what we mean, right, with that. Of course, if the particle is massless, for example, a photon, then pi squared is equal to 0. Now, what I'm saying here is that this could be anything, these two particles. They are going to be on shell, typically. But of course, even if, say, they are on shell and P1 squared is equal to 0 and P2 squared is equal to 0, the sum of the two is going to be something, which is S12, which is different from 0, and I can change it. It's the energy of the process. It's the energy that comes in. Now, if I tweak this energy such that this energy is exactly equal to the mass of this particle here, then this particle is on shell now. These ones were on shell already before, and I can change, right, their energy if you want, but I can also tweak it such that this one becomes on shell, and then I produce a singularity, okay? The other thing that can happen is that I can tweak this energy, instead of being on shell like this, such that these two particles here, that I produce here, you see in the second part of the graph, these two particles go on shell. Imagine that this one has mass m1, and this one has mass m2. I can actually tweak it such that S12 is equal to m1 plus m2 squared, right? So if I do that, it means I have enough energy to produce these two particles. And so what's going to happen, again, this is what physics tells us, I'm not proving it to you, I'm just stating it, is that there will be a branch cut. What does it mean, a branch cut? It will mean that this object, this analytic function of S12 and the two masses, will develop a discontinuity in the complex plane of S12, and typically this discontinuity will look like a logarithm of this type. Typically, it can be a logarithm, or it can be also a square root discontinuity. Okay, there is actually a theorem that tells us that these discontinuities are either logarithms or square roots. So if I go with the energy very close to this, I can produce something like that. Okay, that's what we mean with a branch cut. This is a bit more clear because I will use like this terminology. I will say that maybe I might say that the integral has a branch cut, or it has there is a singularity or something like that. And this is what I mean. Okay. Is there any question about this? Does this look very strange as notation? Yeah. Mm-hmm. No, exactly. This is fixed by momentum conservation. Exactly. So somehow that's what is happening. So if you want here, there is one single particle, and so I can get a pole. if I have two particles, if I produce two or more particles, and then there is practically a loop, if you want here, then here there is also a momentum that flows and that I have to integrate over in the same way as I discussed before, somewhere here. Now, when I do this integral will produce some transcendental function that depends on S12 and 1 and 2, and this transcendental function will have a branch cut. So in that sense, a discontinuity when S12 becomes equal to M12. This is what we mean with a multi-particle state, because two particles are going on shell at the same time, okay, or three, right? It could be more complicated. If the diagram looked like this in this theory, if it existed, then I would have three particles that can go on shell at the same time, and so on, okay? So this is just to say that actually the structure, so what I want to stress with this, even if it looks maybe a little bit odd, is that the structures of the singularities of these integrals that are the objects of study that we are interested in, okay, we compute these integrals that come out of these things, their singularity structures is actually not random, but it's related to physics, okay? So actually learning about the singularity structure is very important because, well, more or less somehow it tells us about the physics, and we also know, if you want, physics can constrain what kind of singularity structure can or cannot appear at the end in our calculation. So if we know that we are not computing a random integral, but we are computing an amplitude, then we know that some things are not allowed to happen, okay? And this typically happens when sometimes you have very complicated cancellations between many integrals, and then finally you see that the wrong logarithms, for example, cancel out. And this is very important because it tells you that if you had been clever from the beginning and chosen a better integral to compute, maybe you would have never encountered that singularity from the beginning, right? Which is one of the reasons why knowing where the singularities are is interesting, and knowing how the singularities show up in the integrals that we compute is interesting. So a lot of the work that we are doing on Feynman integrals, also Andrew over there from different points of view and so on, is actually really to try to relate these things, right? So we want to understand what are the functions that come out of these integrations, how these functions tell us something about the singularity of the process, and now we can actually constrain, if you want, use physics to constrain the type of functions that can appear in the final result, because this helps us to simplify the calculation, okay? This was just a little bit of, yeah, blah, blah, yeah, sorry.
Can you give a motivation from a physics perspective why one does not expect just from a
Well, I mean, from a physics point of view, I don't know exactly what you mean. I mean, it can be proven, right? Even from the point of view, if you want, from the so-called Landau analysis of how the singularities look like, that the singularities that you produce are always of logarithmic or algebraic type. Now, if there was an essential singularity, it would be kind of strange, right? Because these singularities, as I said, they have to do with really how the process, how really the cross-section, if you want, or the probability behaves close to that particular point, right? So I don't know if there is a physics, I don't know, I never really thought about it, if I can exclude it from a physical argument in this sense, but it's definitely proven that these things cannot happen. Yeah, this, you know, yeah. Okay, so this was my little introduction, just to say that this is what we want to do, right? And one of the things that people have understood recently, as I said, is that computing these integrals is not, these integrals are not anything. They are typically can be related to geometrical objects because they live somehow on some sort of algebraic varieties, as we will see later in this class. And somehow that's the reason why somehow we want to make this connection. So we want to understand what kind of functions can appear here, how the singularities are connected to them, and how this can help us to do the calculations in a simpler way. Okay, this is a little bit my motivation. Now, let me try to introduce, I haven't told you yet what these integrals look like, right? I made you some examples. I said that typically you will get these propagators, these denominators. I call them propagators sometimes, that come from these lines. So let me actually make an example, which is a little bit more general than this. Maybe I can actually do it for cleaning the boards here. Let me take a very classical example, which is the production of a Higgs boson in gluon scattering, okay? This is a process that we typically write like this. It doesn't really matter. It means two gluons, which are two particles in strong interaction theory, QCD, collide with each other and produce what we call a Higgs boson. From a point of view of a diagram, we would draw something like this. Gluons are typically drawn as curly lines. Something happens in between, and this Higgs boson is produced, right? This is my gluon, this is my gluon, and this is my Higgs boson. And maybe this has momentum P1, and this has momentum P2, and this, of course, has momentum P1 plus P2, which I might call Q, right? And comes out of this. Now, if I write down a typical representative Feynman diagram for this process, this is an example of a Feynman diagram for this process. Again, you cannot, if you don't know Feynman rules and have not studied quantum field theory, you have to trust me on this. But Feynman rules tells you how particles can interact with each other. For example, a gluon can interact with two fermions. This is an interaction point, this is an interaction point, and this is an interaction point where two fermions can produce a Higgs boson, okay? And this is what we call a triangle graph. Now, in quantum field theory, there's a lot of stuff that comes on top of the nice integrals that we want to compute and that also mathematicians typically like. And this stuff comes from the fact that these particles floating around here are indeed not scalar particles, but they typically have a spin. So they transform non-trivially under the Poincare group. Okay, and this is what actually Bernd was doing for spin 1/2 particles, introducing spin orellicity formalism. In general, this will be spin 1 particle, spin 1/2, and so on. And this is actually pretty nasty. So let me actually try to draw for you what this would look like, just to give you an example. So we have an integration measure. I'm going to call this one the loop momentum. I think I call this one K. And then I have K plus P1, and then K plus P1 plus P2. Right? This is P1 and this is P2. As we said before, the two momenta that go in, and then I have this momentum conservation at every vertex, and of course here I have P1 plus P2 that comes out, right? So then I have to integrate over this K momentum, that is the free momentum that flows around here. And then what do I have? Well, Feynman rules in this case are a bit complicated. They tell me that since there is a fermion loop, then there would be a trace that I would have to do to something like, that are called gamma matrices. I mean, we use like strange notation, but I'm going to forget about this in a second, so don't worry. It will be something like this, K slash plus P1 slash minus M, and then gamma mu2, 1 over K slash plus P1 2 slash minus M. It doesn't matter what all of this means, okay? These slashes are something like a momentum dotted with Dirac gamma matrix, which is what actually Bernd had before. That's why these Dirac gamma matrices are so important. And it's a way how we like to write these things. I don't know. So I just know that the Russians like to call it like this. So this is also an alternative notation with a hat. I don't know if it was Feynman or maybe someone. I think it's probably Feynman because maybe it's called Feynman slash. Yeah, was it him, the first one to use it? I'm not 100% sure though. It was probably Feynman. Yeah, no, of course. I mean, you don't want to write all these gammas all the time, but I don't know if Feynman was the very first one to use it or it was introduced by someone. Yeah, maybe Dirac, yeah. Not a good historian. But there are different notations. What I want to say here is that all this stuff here, all these gamma matrices, Dirac gamma matrices, these slashes, this just means the inverse of this operator because here there's also a matrix at the denominator, right? It's just a way to write an inverse. It doesn't really matter because at the end of the day, what we're going to look at is just the scalar integral that actually is connected to this. So we are going to use, if you want, the fact that, I mean, this would be mu1 and mu2 would be the two external indices associated to these two gluons, but it doesn't really matter too much. We're going to write this as something scalar, which we write as a form factor, and then something that carries all the information about the tensor structure here. And I mean, again, it doesn't matter where this comes from. If you have seen this already, good. If you have not seen it, it doesn't really matter, really. Weird. So this is actually something that tells me that this object at the end is to transform as a rank 2 tensor, and it has to have some specific properties that depends, of course, I mean, depends on the two momenta and so on and so forth. This is the G mu nu, is the metric tensor, it doesn't matter. But I actually want to go and look at what is in here. This object here is scalar. Scalar meaning it does not transform, it transforms trivially under Poincare, okay? What is this thing going to look like? Well, this thing, this F, is going to be made of integrals of this type there will be the 3 denominators here, which now become scalar and look like this. Okay, so the denominators in the end, forgetting about this funky writing, they always like the momentum squared that flows in the line minus the mass of that line. And here I'm assuming that this line always has the same mass, which I called m. Okay, so this particle that goes around here, you can think about it as an electron, as a top quark, as whatever you want, and it will have a mass which we call m. Okay, and this is the mass that appears here. The momentum k is the momentum that we are integrating over, P1, P2, and so on are the external momenta. And then what do I get at the numerator? Well, at the numerator, I don't really get only one, right? Because what I can get out of all the possible things here, if you try to actually write it explicitly like this, are in general scalar products of the loop momentum with itself, of the loop momentum with P1, and the loop momentum with P2. So we get in general a polynomial, okay, polynomial in the scalar products. So is this, I have not really proven it to you, I'm just arguing that this is what it should look like. Is this convincing or does it look completely crazy? Yeah, so maybe. It will be in general an arbitrary polynomial where these things are, if you want, the variables, right? So it could look, for example, like k squared plus 3 k dot p 1, and then, I don't know, k dot p2, and then maybe I need something to have the mass, right? I don't know, and something like that, right? It will be some scalar product of this type. If you try to perform this trace and do a little bit of algebra here, you will see that this actually looks like that. And I think it's kind of reasonable to imagine. I mean, I'm not really proving it, but tell me if this sounds completely crazy, that the only thing that I can get at the numerator, if it's not 1, is going to be scalar products between the various momenta. I mean, of course, I could also get scalar products between P1 and P2. I'm just not writing it here because I don't have to integrate over it, right? So I pull it out. I only take the scalar products that depend on K, right? This one would be part of the one that I wrote here. Yeah? Mm-hmm. Very good question. We integrate everywhere. So if you want to integrate on the full, you can think about it as RD, okay, in this sense. I mean, this is not really completely RD because we are in the Minkowski space in the signature that Bernd described before. So k squared is k0 squared minus, if you want, the remaining d minus 1 part squared, right? This is the metric that we are working in, this plus 1 minus minus. And we integrate everywhere, right? From minus infinity to plus infinity on the whole space. That's the reason why these things are typically divergent if I fix d equal 4. Right? If I fix a specific number of dimensions, I'm going to get divergences all over the place, okay? And this is the reason why we keep d as a generic variable, yeah? And so this is not No, not yet, because this comes on top of that. So the rational part will actually come from this integral still. You see, this is only a tensor part. This is trivial. This only comes from the transformation of the integral under Poincare. Under Lorentz and Poincare transformation, if you want, it has to be a covariant tensor because it has 2 indices, one index here and one index here. And so also it has to be gauge invariant, which is a technical thing, which is the reason why you get this particular combination. But the point is that from this, you get this. And I wanted to say that this is completely trivial because whenever you write a diagram for me, I can tell you immediately what's going to be here. There could be more of these structures, but they're just general, if you want, this is a so-called tensor decomposition of all the possible objects that you can get that transform properly under Poincare. Exactly, but then in front of it, I will get an integral, which will be a complicated combination of, as I said, a polynomial at the numerator and some denominators, okay? And this is now, there will be many of them, right? It will be a sum. So if I separate it, I get many integrals, or one single integral if I put everything together. But this is the object that now itself will produce rational functions and transcendental functions. okay? And is the object that will tell us, for example, if the energy of these two particles is exactly equal to the mass of the sum of the masses of these two particles, this thing has to diverge, has to produce a branch cut, as I was saying before, as a logarithm, right, connected, if you want, to this so-called threshold here, so to the energy that we need to produce these two particles, okay? So the reason why I was going to say this is that we are only really looking at the scalar part. We are forgetting about everything else. So I'm practically forgetting about everything that, in a sense, also you were talking about, because it's also connected to Lorentz and, if you want, Poincaré part. Okay, so these are the objects that we are thinking about. So we are thinking about integrals that have denominators of this type connected to the lines that we can draw. So I don't care in the end if the particles are gluons, scalars, fermions, whatever. I'm just going to draw the various propagators like this. And then I will have, in general, we'll have to think about what is the most general polynomial here, and what can I say about this polynomial. Okay, this is the object of study. Is this clear? Because if this is not clear, then we are not going anywhere. I don't know if I said it in a in a clear way. Yeah. Let me maybe try to swap this. This depends on the if you want, on the process itself, not even on the individual diagram. For example, if I have two gluons that produce other two gluons, or two gluons that produce a Higgs boson and three gluons, whatever, just knowing what is produced, so what is scattered and what is produced, tells me what that is going to be. And then I can have like hundreds or thousands of Feynman diagrams, all different integrals that will all have the same prefactors in front. That's why I can forget about them and only want to look at the integrals, right? And whether, for example, I'm doing this calculation with so-called one loop or two loops or three loops, higher and higher orders in perturbation theory, also that structure is not going to change. The only thing that is going to change are these integrals, which will be more and more complicated, and we'll have to integrate more and more times, okay? That's why that part doesn't really matter for us. And it's actually the easy part somehow. And I don't want to talk about it because, I mean, one could have a set of lectures just on that, okay? That would end up probably with introducing spin-orellicity, formalism, from the point of view of the physicist and not the mathematician. Okay, now I have to get you used to another thing, namely to the fact that I'm going to do very often the following thing. So imagine we have our graph, which now I can really write schematically like this, because it doesn't matter anymore whether the particles are gluons or anything, right? And this is connected to this notation over there. So what do I do? Well, typically what I'm going to do is that I'm going to call these propagators or these denominators, I'm going to call them D. So I will have three of them, D1, D2, D3. Okay, in this case, of course, D1 is k squared minus m squared. In the particular case we are looking at, D2 is this, and D3 this, right? In the specific example that we have, but in general, if we have more, I'm just going to call them D. This is a notation. And then I said that the numerator, I have all the scalar products. There are three of them, right? And I have a polynomial in the scalar products. Of course, I mean, it's clear that this is one-to-one. I mean, I can express these scalar products in terms of these Ds, if I want. And this is something that we are going to do very often, okay? So in particular, I can say that k dot k is D1 plus m squared. K dot P1 is 1/2 D2 minus D1 minus P1 squared. That would be the square of this momentum, which if we choose to be 0 is not there. If it's on shell, if it's an on-shell gluon, but it could also be different from 0 in general. And then the last one is D3 minus D2 minus P2 squared minus 2 P1 dot P2. And again, if I choose the two initial momenta to be equal to 0, which is what typically is for gluons, okay, now we are going to work in this particular case, then these two terms are not here, right? So this is one thing that I can always do. In particular, when I look at what is so-called a one-loop graph, or one-loop integral, this is always possible. I always have as many propagators or as many denominators as is the number of scalar products that I can build. So I can always express all the scalar products in terms of the propagators or vice versa, right? This is true at one loop, okay? So in this case, it means that the integrals that I'm interested in, the scalar integrals, are actually integrals of this type. I'm going to introduce the following notation. Right? Because I can rewrite, I told you that I'm going to get polynomials in those things, right? In those scalar products, but the scalar products I can rewrite them in terms of the d's. So it means that I only need to consider integrals which have these three d's elevated to possible, raised to possible powers, where these ai's, if you want, they can be in z. So they can be positive or negative, right? They could also be a denominator in principle, right? So this is a very common notation. When these a's are positive, then we know that they are at the denominator, so they are normal denominators. When you get something negative, it means that there is something at the numerator here, right? This is also a pretty common notation when we discuss about Feynman integrals. And as I was saying, this is always true, okay, at one loop. It's actually a relatively easy combinatoric exercise. Imagine that you have P1, P2, blah, blah, blah. Let me write it like Pn minus 1 Pn. So you have something that has only one single loop, okay? And you have n momenta attached to it, n external momenta. Then, of course, you can see that you are going to get n propagators. Di's, okay, 1, 2, 3, 4, etc. If you count, you see immediately they are n. Of course, like this was like 3 momenta, 1, 2, 3, and you get 3. If you have 4, you have 4. If you have 5, you have 5, and so on and so forth. And you're also going to get n scalar products. Yes, sorry. Yeah, tell me if I write something strange. So n momenta and n scalar products, which of course are k dot k and k dot pi, right? Of course, I have n momenta, but one of them is not independent because of momentum conservation. So these are like k dot p1 till k dot pn minus 1, right? So I have n of them and n of them, so I can always express one in terms of the other. And so we will always write one loop integrals like this. So in this case, it will be a1, an, and this will be an integral over the loop momentum, which we typically call k, and then 1 over d1, a1, dn, an, right? So this is notation for now. Again, I mean, I'm not really talking about whether these integrals are convergent or not, okay? I want to stress it again for mathematicians if you have never seen it. I don't know if there is someone that has never seen this. Maybe it's the case. One can, if you want, define this procedure that is called dimensional regularization, which can be defined either axiomatically or also really practically through a parametric representation of these integrals, which we will discuss tomorrow. Where we really do an analytic continuation in D, okay? So this becomes really a function of the number of dimensions. Now this D is not one of these Ds, I hope it's not confusing, but it's this D. And this D can be really a complex number, okay? So this becomes, we will see an analytic, actually a meromorphic function of D, which will have only poles, okay, in D at most, but it will be analytic otherwise, like the gamma function, for example. And we are going to think about these objects like this as a function of D. Okay. This is very important because it's behind the fact that these integrals practically are always convergent in this framework, even if I'm not really proving it. And therefore, we can do with these integrals whatever we want, okay? So practically they are convergent, so we can manipulate them as you would manipulate any convergent integral. We can do integration by parts, substitutions, split them, sum them, partial fractioning, separate them, re-put them together, whatever we want. Shift momenta in one piece and not in the other one, yeah. Okay. I'm considering this integral over... So this integral is a function, if you want, it would be a function of the, so the integral itself is, you can think about it as done in a sense on RD. It's not exactly RD because it's, as we said, it's with this different metric, but of course, I mean, you can always go to so-called Euclidean metric doing a change of variable somehow. So you can think about this as integrals in RD, that's not a problem. After I do the integral, then the integral will be function of D, of course, right, itself. And I'm thinking, the point is that I'm thinking about this D as a complex variable. Okay? Okay, one important thing to notice is that what I just told you... sorry, yes. Mm-hmm. Well, it will be a sum, right? So I can consider any integral with any monomial separately. So what I'm saying is that when I want to compute, if I want to compute that thing, I will have to compute integrals of this type, possibly a sum of them, right? There could be thousands, millions, sometimes billions of these integrals, okay, in a complicated calculation. Yeah, another thing I wanted to say is that the situation becomes a little bit more general when I'm not at one loop, but say at 2 loops or 3 loops or L loops in general, okay? Then it's not always true that the number of scalar products is equal to the number of propagators. So I have to generalize my notation a little bit if I want to do arbitrary loop integrals, not just at one loop. And I invite you to try to do this as an exercise. If you want, we can discuss this also. So imagine that instead of having one loop, we have an integral, so a scalar integral at L loops. Okay, so for example, imagine you can think about something like this. This is a 2-loop integral, or you can think about something like this. This is a 3-loop integral, a box with 3 loops, right? Here there is one loop here and one loop here. Here there are different loops and so on, okay? And let's imagine that this is also at an endpoint integral, which means this would be a 2-point because it has 2 legs. This would be a 4-point because it has 4 legs, okay? It's again just notation. It means that there are a number of legs, or if you want, you can imagine the number, so n particles, okay? If you want, if you don't like endpoint. Then the number of scalar products, just a simple combinatorial exercise, rho, is equal to L n plus L over 2 minus 1/2. Okay, this is the number of scalar products you can create among the different loops and the external momenta, the independent external momenta, which are n minus 1, not n. Okay, and of course you see that if L is equal to 1, we get rho equal n, which is the case that we had before, right? For one loop, number of scalar products is equal to the number of points. But in general is non-equal, right? So it means actually in general is larger, as you can see from here, right? This is a 1, and this is the number of loops. In general is larger. And so what we have to do is that we have to allow for the fact that there will be some scalar products that we cannot write in terms of denominators. Let's do again an example, right? Exactly this one here. If I have a momentum that enters here P and goes out here, then let me call this one K1. This will be my first loop. Then I will call this one K2 and goes in this direction. And so this will be K1 plus K2 plus P, right? And so you see that I have in this case L equal 2, N equal 2 because I have 2 points, right? And so rho, if you compute it, turns out to be 5. Okay, and in fact it's true. I mean, I get like K1 squared, K2 squared, K1.K2, K1.P, and K2.P, right? I have 5 possible scalar products, but I have only 3 denominators, right? So I have to be a little bit more general. And this is what is called, where we use typically the following notation. We write an integral, so you might encounter this notation here. This will have 3 propagators, so let's call them d1 to the power a1, d2 to the power a2, d3 to the power a3, okay? But then I will also have 2 extra scalar products, S, okay, which are the scalar products I can choose, okay? It's not unique, the choice that I can make, that I cannot express in terms of these 3 propagators. I mean, clearly K1 and K2 squared are fixed, are these ones too, right? But then, for example, I could use this one to express K1.K2, or I could use it to express K1.P or K2.P, right? And then the other 2 will be independent, yeah? And these are the S. Now, these SJs are called irreducible scalar products, or ISPs, okay? Again, just to give some notation. People like to call them like this. Of course, since I'm free to choose these SIs as I like, what is the most typical thing to do? It's not always the best, but it's very typical, is to actually choose these scalar products as other denominators. So to introduce some propagators extra, which were not there at the beginning. And so say, in this case, I have d1, which was k1 squared minus m, if that particle has a mass m, then d2, which is k2 squared minus m, d3, which is k1 plus k2 plus p squared minus m squared, right? These are my 3 propagators. Then now I could add either say s1 k1.p and s2 k2.p. This is a possibility, right? Or I could actually define a d4, which is k1 minus p squared, and a d5, which is a k2 minus p squared, or in any other way I like, that looks a little bit more like a propagator, right? And if I do it like this, which is also very common, then also at more loops, I will write my integral like this, right? I will always write it as a L that goes from 1 to L, the number of loops, dkl d, 2 pi to the d, and then 1 over d1 a1 dn an, right? So I will write the same notation in the same way. But I have to remember that some of these d's, typically the last ones, might be some extra, right, that I introduced like that, right? It's not necessary, but at the end of the day, this is the notation that I'm going to use because it's more compact, right? So I'm going to call all of them d's, but they might come from something like this, okay? That's what I wanted to say. They're actually secretly extra scalar products, but any questions about this, about the general notation? Mm-hmm. Mm-hmm. So for this notation doesn't matter. first of all, right? I think what Bernd is talking about is that, for example, I could do something, say, this is a planar, so-called a planar double box, and this is an example of what is called a non-planar two-loop double box, right? In some theories, typically when you have color, you can argue that these integrals, the type of the scattering amplitude, the part of the scattering amplitude proportional to these integrals is suppressed, okay, or it should be suppressed actually by the, if you want, these are computed typically in SUN and is suppressed by 1 over n of SUN. This can be proven, okay? Unfortunately, very often in real life, it happens that these ones are suppressed by 1 over n, but first of all, in real life, n is equal to 3, so it's only 1 over 3. It's not that bad. But then the coefficient of 1 over 3 might be 3 times larger or more than the other one. And so at the end, these things might be as large as these ones. So there is a lot of actually studies of planar graphs, in particular in N=4 super-Yang-Mills, supersymmetric theories. Here you can define an integrand in a unique way because you have a unique parameterization, if you want, of the loop momenta that you want. And so these are very nice from this point of view. But the type of techniques that I'm discussing, they are more general, right? They can be applied to anything. This is true both for this one and for this one. The number of scalar products and propagators don't change. And unfortunately, I mean, we know of more and more cases where really these ones are as important as these ones in real life. So unfortunately, while these are more beautiful, these ones cannot really be neglected if you want to do a calculation for a collider, typically. Yeah. So that's also an interesting, but of course we typically always start from computing these ones because they're a bit simpler. Any other questions? Is the notation clear? I mean, I really didn't say too much today except notation, but we are going to write a lot these I's like that, and this is what is meant, right? These are the integrals that we are looking at. Now, I don't have a lot of time left, but I wanted to say at least one more thing. I have 15 minutes, but in principle, we're supposed to be questions, but there were already questions. So. Well, you stop me when I should stop, okay? I was hoping to be a bit faster, but that's okay. I think as long as we are all more or less on the same page. I mean, if we are not, please tell me, because I prefer to spend a bit more time. Really a pity if we cannot talk to each other just because we don't understand something very simple that I'm saying, but it's just a strange way I'm saying it. So these objects here, okay, when we have like a full set of propagators that allows me to express all the integrals in the problem that I'm looking at, this is what we call a family of integrals. Or if you want, integral family. Okay, so typically when we want to compute something, we need to identify the corresponding integral families, and we need to compute all the integrals in that family, okay, in order to solve the problem completely. Notice also that, imagine that I'm looking at what is called a box family, so something that comes from a process like this, where I have two particles coming in and two particles going out, and there is a box type graph. Then notice from here that since I can have, I mean, at one loop we said the number of propagators is equal to the number of scalar products, and I can produce numerators, polynomials, in these propagators, right? So this means that in general, in the amplitude that I'm computing, or in the observable, in the quantity that I'm computing, I will not have the box only, but I will also have integrals that I can obtain removing these propagators in all possible ways, right? Because I have like something like this, but there is always a numerator on top of it, right? So of course the numerator is written in terms of the d's themselves, and so some of the d's will cancel, right? So it means if I want to compute these, it also means that I need to compute triangles. Let me try to draw them like this, because this is also a notation that we use relatively often. Okay, what I mean with this is that there are 4 triangles hidden in this box. This triangle here is obtained by removing this propagator or pinching it. Okay, and that's why there are 2 legs that come here in the same point, which are these 2 original legs, 1 and 2, right? I mean here, and here I have 3 and 4, and I have 3 and 4. Right? And of course, I can do this pinching in all possible ways. So in general, I will have 4 triangles, but I will also have, in general, bubbles, which I obtain pinching, the other legs. And of course, this one is equal to the one that I get pinching this one on the other side, right? This one and these ones are equal, and this one and these ones are equal, and give me this other bubble here. And then I can also pinch another one if I want, and then I get down to what is called the tadpole. Okay, so these are called tadpoles. These are called bubbles for obvious reasons. These are called triangles. These are called boxes. And of course, the same thing happens in a much more complicated way when I am at L loops, because I can pinch things in very different ways. And this is sometimes called the family tree. Right? Because I have my integral family, which was a box family, and these are all the integrals that can appear in that calculation that is that refers to this integral family, and are typically called the family tree of integrals. Right? That's one way to call them. I find it actually a cute name. Yeah. Mm-hmm. Yeah. Mm-hmm. You want to compute them as general values of the A's. Yeah, this good luck with that. It's very, very difficult. So I mean, it is possible. If you can do that, you can try. You might also get that the limit for A going to 0 or something like that might be divergent too. Might not be smooth in general, because integrals which are different, which have different A's, might or might not produce divergences that were not there before. For example, a box integral is not divergent when when k goes to infinity, the so-called UV divergences, but a bubble is. And this has to come up from the way you take this limit. And this might be very non-trivial, but in principle, you can do that. Unfortunately, doing this calculation for general values of the A's is very difficult. So what I meant here, this is maybe a good point that is coming out, is that really I mean to compute this for all integer A's, for all A's in Z. These are the ones that matter. I don't need A equal 3.2, right, typically, right? So I need A equal 1, 2, 3, 4. So I really, what we're going to do is that we're going to decide or to find a way to compute all these integrals for all the possible integer values of the A's. Okay? That's simpler, typically. Then you can, of course, try. In some cases, it's possible to compute it for general A's. Yeah? Okay, so maybe I want to close with this last thing, because it is actually connected to your question. Indeed, there are a lot of these integrals. If I really think about them as the integrals with all possible values of A's, not just as a single integral, but all of them, where the combinatorics is very large. And of course, it's bounded because I cannot get arbitrary negative powers here, because there is actually, if you want, amplitudes have to respect some properties, they are renormalizable, and so on and so forth. I mean, the numerator is fixed, the power of the numerator, and also the denominators actually get very rarely squares here. Typically, these are linear. Okay, all these A's at the denominator are typically 1, except in special cases. And then I have some positive, or if you want negative in this sense, some of them that go at the numerator. Okay, but still the combinatorics is very large. So let me give you an example. Okay, imagine that you want to compute two gluons that produce two gluons in what is called quantum chromodynamics. Okay, so the theory of strong interactions. Then you get at one loop something of the order of 100 of these integrals. I don't remember the exact number, okay, that you have to compute. There will be some sort of a box family here and some possible permutations, okay, and you get something of the order of 100 integrals to compute with different powers, 0, 1, -1, so on and so forth. If you go to 2 loops, then the number of integrals grows to something like 10 to the 5, okay, no, actually 10 to the 4, sorry, integrals. And if you go, for example, to 3 loops, which is the highest order that has been computed for this process, you get something like 10 to the 7 integrals, organized in different families and so on, okay? So clearly, you don't want to compute all these integrals one by one. It would be nice if you could compute them as general values of the A's, but as I said, this is very difficult. So what we actually try to do is that we try to to look for relations among these integrals, okay? And this is the very last thing that I want to say, and then maybe we start back here tomorrow. This is one of the most important things, that is maybe the most trivial thing if you think about it from a mathematical point of view. But when people realized this, it was in the 80s, okay, this was really a revolution in the calculation of Feynman integrals, is that Feynman integrals, and it's very important in dimensional regularization, fulfill integration by parts identities. Now you're going to tell me, of course, what is the revolution? Integration by parts identities, we know they are true, right? For a very long time that I can do integration by parts. The point, and these are called IDPs, is that, and I'm not going to prove this, okay, is that since the integrals in dim-reg are always convergent, okay, because of the way we define this operation, you should really think about this as a functional, as I was saying. So it's an operation that acts on these things and gives us a function out of it, okay? And this functional can be defined properly if you want axiomatically, or we can also do it differently, as I said, next time. With this operation, one of the properties of this operation that I want to be satisfied are integration by parts identities in order for this to really look like an integral, which means the following. It means that if I take any of these integrals, say at L loops, and I differentiate with respect to one of the loop momenta, I put any other momentum here so that I get a scalar. These two indices are contracted. And then I have 1 over E1, A1, Dn, An, okay? This quantity here, the way physicists typically think about it is that they think about Gauss theorem in d dimension. So it's kind of the integrand evaluated at the boundaries. Okay, but now this integral evaluated at the boundary, since the integral has to be convergent, it has to be 0. Okay, this is not the only way to think about this, but the idea is that whatever derivatives I do and whatever other momentum I put here, it could be one of the external momenta or one of the loop momenta, it doesn't matter here. If I perform this differentiation, I have to get 0 at the end. Because you can think about it as Gauss theorem. It's not the only way to think about this. Another way to think about this is that in this integration, I want actually to be able to do general transformation of variables. I want to be able to shift the loop momentum, right, to do something like KL that goes to, I don't know, some transformation, some matrix, right, that reshuffles the momenta. And these linear transformations, they don't have to change the integral, right? So the generators of the linear transformations are exactly the derivatives of the momenta. This is what is actually happening, is that this corresponds also to the fact that I can do arbitrarily linear transformations on the integral. And so this is why this has to be 0. Now you can think about what is the best way that you like to think about it. Some people like to think about it as Gauss theorem. Some people think about it as transformations, linear transformations, okay? The reason why this is nice is that you see what happens when I differentiate with one of the loop momenta, these things, I'm going to get integrals in the same family, right? I'm going to just change these powers and get some numerators, but the numerators are scalar products because they are contracted with one of the momenta, again. And these scalar products, I can rewrite them in terms of the d's, right? So I get out of this an equation which relates integrals of the same type. And I can write as many of these relations as I want for different values of the a's, okay? And I get a big system of equations. And I mean, this thing was actually realized first by Chakov and by Chetirkin and Chakov. Maybe I can write it here. IDPs by, I don't know if I'm pronouncing the name properly. I apologize if there are Russians in the room. Okay, and then what was realized next, and this was actually many years after by Laporta in 2000, is that if you, I mean, initially people really tried to write these identities as for general values of the A's and try to solve them as recursion relations. You practically get recursion relations, very complicated ones, and you try to find, it's like people were calling this multidimensional chess at the time, I remember. What? Trump. You use this term? I don't know. Sorry about that. I didn't want to make a citation. I didn't know about that. So I take it back. Maybe I should remove it. Sorry. But that's how people were calling it, because really they were trying. I mean, imagine you have like a given number of loop momenta, a given number of propagators. You write all the possible identities with general values of the A's, and then you try to find a recursion relation that allows you to express as many of these integrals in terms of as many as possible. For example, to reduce these powers, so to reduce the numerators and so on. Then this guy, Laporta, in year 2000, realized, well, it's much simpler in general to really produce these identities for specific values of the A's, okay? So really you produce a lot of them, like hundreds or thousands or millions, put in all possible values of A's that you can think about, all zeros, 0, 0, 1, 0, 1, 1, 0, and so on and so forth. You get a big system of equations and you feed it to a computer. What happens is that the number of integrals that you produce on the right-hand side grows less fast than the number of equations that you can produce. And so at some point, the system looks over-constrained. You have more equations than integrals, but actually many of these equations are redundant. And so you can express all this big number of integrals in terms of a basis of integrals, which are called typically master integrals. Okay, we're going to do an example tomorrow, so that this is not, because now it's over. So through this so-called reduction procedure, I'm writing very badly today. We produce all these identities, we get a big system of equations, and we try to solve them, okay, one after the other. And then we see that all the integrals, the more identities I produce, the more integrals I can solve, all in terms of a basis of integrals, which are called master integrals. This is really, you can think about it as a basis. And now people have proven that IBPs have actually a Lie group structure, and through this Lie group structure, they can prove that the number of master integrals is always finite. Okay, so in every case, you're going to have whatever type of integral family you imagine to study. If you do this reduction procedure, you will always end up with a finite number of integrals that are the basis of your problem. Okay, now this, I didn't have time to show you an example. I will show it tomorrow. Okay, so then I hope that this becomes a little bit more clear. We will do an example of a master of this reduction, but this is how we are saved, right? Because from the problem that I had before, I don't have the numbers anymore. But the numbers that I had before were something like 100 integrals at one loop, 10 to the 4 at 2 loops, and 10 to the 7 at 3 loops. If you do this reduction procedure, you discover that these ones can be solved in terms of something like 5 integrals, order of magnitude, so it's okay, pretty good. These ones become something like 15, again, order of magnitude, and these ones become something like 500, okay? So 500 is still a lot, but it's definitely nothing comparable to 10 million, right? So we can, of course, hope to compute 500 integrals and not 10 million. Okay? We're going to discuss this tomorrow, and then we continue from there. Sorry if I was a bit late, to be honest. Yeah,
you are perfectly on time. Thank you.